Okay, this is the last section in the book that we're going to cover, section 7.4, over parallel lines and proportional parts. There's kind of a lot in this, lots of different things just kind of join. They didn't fit with anything else. They put them together in one section. And yes, dealing with parallel lines quite a bit. And here's Charlie Brown saying, ever notice that the number of people watching is directly proportional to the stupidity of your actions? So basically, the more ridiculous of a mistake you make, the more likely more people are to be watching. All right, triangle proportionality theorem. You at least need to draw the picture and probably have this written in this part right here. You don't have to write out those words. I don't think you'll actually read the whole words again, but let me read them out loud to you right now. If a line is parallel to one side of a triangle and it intersects the other two sides in two distinct points, then it separates these sides into segments of proportional lengths. Okay, so basically I've got parallel lines here, and BA is proportional to CB, so now DE has to be proportional to CD. All right, and that's how you're going to set up your proportions there. I mean, that's not the only option. You can say BA is proportional to DE, and CB is now proportional to CD. I mean, there's lots of options within that, but that's what you're looking at. Okay, now we're going to use it. They tell us triangle RST, they have parallel lines. RT is parallel to VU. SV is 3, this piece right here. VR is 8. UT is 12. And we need to find SU, which is X. They've already marked that for us. Okay. So basically V to R is 8. And I can compare 8 to 3 or 8 to 12. It doesn't matter. I kind of like to go across for some reason. 8 to 12, so this piece is proportional to this piece, as the 3 is, I'm going to put a different little symbol, 3 is to X. Okay? That doesn't mean somebody else couldn't write, and they could. They could write 8 to 3 is the same as 12 to X. Doesn't matter which way you go, but when you cross multiply, either way, you get 8X equals 36. Okay, so then divide both sides by 8. 8 times 4 is 32. We have 4 left over out of 8 parts, so that's 4.5. So X is equal to 4.5, which is the distance from S to U. Example 2, we have another triangle. They tell us that AC and XY are parallel. They've marked it on the triangle. They tell us AX is 4, XB is 10.5, CY is 6, and BY is X. So I'm going to say 4 is to 6 as 10.5 is to X. You could also say 4 over 10.5 is the same as 6 is to X. And there's about 2 other variations on the same thing, but if you cross multiply, either way, you are going to have 4x equals, is that 63? 10.5 times 6. I better just double check. Oh, I'm not right. In 1.05. 10.5 times 6 is 63. Divide both sides by 4. And I wrote down a 6, but I really mean a 4. 4 goes into 6 once. I got 2 left over, so 23. So I got and 3/4. So 15 and 3/4, or you could say 15.75. All right. All right, here, the converse of the triangle proportionality theorem. So basically, it's the reverse of what we just had. So in other words, if you find out that BA is proportional to CB and DE is proportional to CD, then you could say the lines are parallel. Where in our previous rule, if the lines were parallel, then your sides had this little proportional thing going on. If the sides are proportional now, then you have parallel lines. So at least your picture and probably this example written there will be sufficient. All right, example 3. In triangle DEF. DH is 18, so we better write that in. HE is 36. DG is 1/2 of GF. Ooh, whatever this is, we're going to take half of that. So wouldn't this be congruent to this? Don't you think? Yeah. And determine whether GH is... Oh no, I can't put that down. Undo. Mrs. Talley did a big mistake there. It's half of the full length of, or half of GF. Okay, so this amount right here, I don't know, so I'm going to put X, so this part right here is 1/2 of that. Oh, look at that, determine if they're parallel. Well, is 1/2 of X equal to 18 and X equal to 36? Isn't this half of this? And this is half of this. So they have to be proportional. So I would just put in my own words. I say if this DH is half of 36 and DG is half of the GF, then they are both proportional and therefore my lines are parallel. All right, example 4. Triangle WXZ, XY is 15. YZ is 25, WA is 18, and AZ is 32. Now I need to prove if they're proportional. So I'm going to say, there's lots of ways to do this. 18 to 15 is the same as 32 to 25. So that's one way. If you looked at this and thought to yourself, hey, I'm going to compare 18 to 32 and then over here compare 15 to 25, that's okay as well. When you cross multiply, either way, you are taking the 18 times the 25 and the 15 times the 32. All right, 18 times 25 is 450, and 15 times 32 is 480. So those are not equal to each other, so they are not proportional. So are my lines going to be parallel? No way, Jose. They are not going to be parallel. All right, so I do not have parallel lines because these pieces are not proportional. All right, here we go. Triangle mid-segment theorem. And you've actually talked about mid-segments before when you dealt with the trapezoid. Let me quick take you down memory lane. Woohoo! All right, there's a trapezoid. And then you found the midpoint, and the midpoint, you added up these two, and then you took it times half, and you got this length in the middle. A mid-segment of a triangle is not much difference, okay? Your mid-segment, you find the midpoint of one side, the midpoint of the other side. That is your mid-segment. Make sure a picture like this gets in your notes. Now, I'm going to put little markings to show that that's the middle, and over here for this being the middle. Oh, that's kind of like that picture up there. All right? What this basically shows us that this is 1/2 of this, okay? Maybe I should draw the arrow the other way. All right, so if this is 100 centimeters, then this will be 50 centimeters. That's just the way that works. That's the rule of mid-segments. All right, let's use it. Example 5. Triangle ABC has vertices. All right, they got them marked down here. They got them labeled. DE is a mid-segment. So that means this piece is congruent to this piece is congruent to this piece. So it's a mid-segment of the triangle. Find the coordinates of D and find the coordinates of E. So it's the middle of this line. It's the midpoint of this line. There's a formula. We knew it as the midpoint formula. Now let's take a little walk down memory lane. What is that formula again? X1 plus X2 divided by 2. And then you have Y1 plus Y2 divided by 2. That's your new X and Y values for the midpoint. Oh yeah, you've seen that before. Well, let's use it. So I'm going to find the midpoint using these two. So I'm going to take my X values and add them together. So that's -2 right here. And then my other X value is 2 plus 2. And I'm going to divide it by 2. And then you're going to take this 2 and this 4, add them together, because they're my Y values, and then divide by 2. So -2 plus 2 is 0. 2 plus 6 is 8. Well, never leave anything non-reduced in Mrs. Talley's class. 0 divided by 2 is just 0. 8 divided by 2 is 4. So the midpoint right here makes sense, is at 0, 4. You're like, well, hello, isn't that like a y-intercept? It's on the y-axis. So 0, 4 makes perfect sense. All right, I also have to find the coordinate of E, this one right here. So I have to find the midpoint of this and this point. So I'm going to add my X values together. So I'm going to have -2 plus 4, and then you divide it by 2. So that negative 2 and this 4. But our numbers are almost too similar here. All right, and then I take your y values, the 2 and the negative 4. So 2 plus negative 4 and divide by 2. This reduces down to 2 over 2. This becomes negative 2 over 2. Reduce further, I got 1, negative 1. Does that seem reasonable? Well, yes, it does. So my two answers here, one midpoint is at 1, negative 1. The other midpoint is at 0, 4. And that's what I needed to find, those coordinates. All right, happy example. Moving on to the next one, example 6. Triangle UXY has these vertices, they're marked, they're labeled, it's beautiful. WZ is a mid-segment. And they want to know, is WZ, is this right here actually 1/2 of this? So I have to know how long this is. I wonder how far it is from W to Z. I wonder what the distance is from W to Z. I wonder how I can find the distance when I'm looking at a set of points up there on a coordinate graph like that. Distance formula. All right, so distance formula, I'm going to have to use that to find this distance, and I'm going to have to use it to find this distance. But I can't find this distance unless I know what my points are. How will I find my points? I will use the midpoint formula. So let's start there. So I'm going to take the midpoint of these two. So I have negative 3 plus 3 over 2. That'll be my x values. My y values are 1 and 3. Add them together, divide by 2. Now I have 0 over 2 and I have 4 over 2. Simplify again. I got 0, 2. That is that particular point. Now I'm going to do it again with negative 3, 1 and 5, negative 7. So negative 3 plus 5 divided by 2. 1 plus negative 7 divided by 2. Reduce. I have 2 over 2. I have negative 6 over 2. Now I have 1, negative 3. That is the coordinate of this point. Point Z is at 1, negative 3. Okay. Now we do the distance formula. You're like, this is Talley, I forgot. I haven't used it for like a whole chapter. All right, well, let's go back and refresh ourselves of that distance formula. It doesn't matter which comes first. I think I'm just going to put x's. And remember, I don't really care too much about the little 2's and the little 1's. I think it's technically x2 minus x1 squared, and then y2 minus y1, quantity squared. But these can be y's, these can be the x's. It could be 1 minus 2 and then 1 minus 2. And I don't, just as long as you're consistent when you work it out. Okay, let's give ourselves some space. I am first going to find the distance from W to Z. We'll do that. We'll use these 2 points right here. Since I wrote x's first, I guess I'm going to do x's here. 1 minus 0 squared. And then I take my y's. Negative 3 minus 2 squared. You use the distance formula so much in geometry, which is a good thing because you're going to need it for your ACTs, your NCAs, all your NPSTQ3s or whatever test you're going to take. So make sure you don't lose it. And we'll make sure that by using it. All right. And then we take negative 5 and we square it. Be careful. These should always be positive numbers. I have kids who type this in, something weird in their calculator. They don't put parentheses and come out with a negative 25. It will always be a positive. These under here. We should have 1 plus 25. I'm going to write square root of 26. I will not bother to take the time to put that in a decimal form because I'm going to find out if the other one is square root of 52. Because it's got to be half this distance right here. So now I got 3 and 3 and 5 and negative 7. Here I go again. Here I go again on my own. I'm going to do my x's again. 5 minus 3, quantity squared. Negative 7 minus 3, quantity squared. So now I've got a 2 squared, and I've got a negative 10. Oh, be careful. It's a negative 10 times negative 10. So now I've got a 4, and I've got a 100. Now I got a square root of 104. Ooh. If I take that, divide it by 2, will that give me square root of 26? I do not believe so. And you can do it on your calculator if you want. You can take the square root of 104. I'll just tell you right now, if I take the square root of 104, I get 10.2-ish. Okay. And over here, the square root of 26 comes up, ooh, maybe I should be careful when I'm blabbing away. 5.1. Oh, you know what I was thinking? Because of the divide by 2 part, I was getting really messed up. Oh my gosh, would you say that 5.1 is half of 10.2? Even though I said earlier, square root of 52, I actually need the square root of 104. So, would you say that is a mid-segment? And you would have to say yes, it is, because it is half the distance. That's crazy. Good thing I went through and followed through with that. Otherwise, I'd have all my class messed up with that. All right, on to the next one. Oh, we got more rules. If 3 or more parallel lines intersect 2 transversals, then they cut off the transversals proportionately. All right, so let's see here. Make sure you draw the picture. And what I'm going to do is put in little squiggles again. AB is to BC as DE is to EF. Okay, that's one way you can look at that. I'm going to clear that out. Watch this. AC is to DF as BC, so you can just pick this little piece right here, BC is to EF. Okay, there's lots of different proportions. Let's clear that one out. How about AC is to BC, just do like right below it, the same as DF would have to be, is D all the way over here? I'm writing it as it is, and it's not really. Let me, I don't want to redo this whole video here, so you're just going to bear with me. AC is actually from here to here, sorry. And then DF is from here to here, all right? And then BC is from here to here, and that is proportional to EF. That's one way, and let's do another one correctly here. So now AC, which is from here to here, is the same as, not the same as, is proportional to BC, just as DF would be proportional to EF. Whew. All right, let me clear that one out. If 3 or more parallel lines cut off congruent segments on one transversal, then they cut off congruent segments on every transversal. Basically, that's saying if you know that this is congruent, if DE is congruent to EF, then AB is congruent to BC. It has to be later on down the road. Okay, with that said, let's move on and try this out. Okay, so I can say 13 is to 26 as 16 is to x. I can say 13 is to the full length, which is 39, as 16 is to the full length, which is 16 plus x. Yes. Or I can say 13 is to 16 as 26 is to x. So that's what I think I'm going to do. Okay, some of you were like set on the first one I said. If you were like, hey, 13 is to 26 as 16 is to x, if you will notice when you cross multiply either one of those, you will have 13x is equal to whatever 26 times 16 is, and I'm getting 416. Okay, and now I'm going to divide both sides by 13, and I'm getting 32. So x is equal to 32. And I don't need any labels, I just needed to find x. Okay, that seems fancy schmancy enough. In example 8, we got a very similar problem. Davis Broad and Main Streets are all parallel. Okay, so I'm going to put a little mark here to show that they're all parallel. The figure shows the distances in city blocks that the streets are apart. Find x. Once again, I'm just going to say 24 is to 15 as 8 is to x. I could go crazy. I could do 24 is to 8 as 15 is to x. Either way, it's going to work. I cross multiply. I think this is 120. All right, divide both sides by 24. Okay, 120 divided by 24 works out to be just plain old 5. And that's all I need to do is find x. And our last example here deals with the parallel lines, and if you have congruent segments here, if I know these are congruent, then these have to be congruent, which is good, because if I want to find x, I just set those equal to each other, because they're congruent segments. Solve for x. I'm going to subtract 3x from both sides. Now I'm going to subtract 2 from both sides. Now I'm going to solve for x by divided by -1. So my x value is 6. Oh, you guys love fractions. 8/3 y plus 7 is equal to 5y. All right, I gotta get my y's on the same side. I cannot move 5y, otherwise I'm gonna have an uneven equation. Minus 8/3 y. I like to work through fractions, although I know most of you are grabbing your calculators to work it through as a decimal. But isn't 15/3y the same as 5y? Oh yeah, it is. And don't I have a common denominator? The purpose of changing it to 15/3. And now I have 7/3 y is equal to 7. And now we're going to get y by itself. So I take it times 3/7, take this times 3/7, and now y is equal to 3. If you did that as a decimal on your calculator, you might end up with 2.9. If you write that down, it will not be correct. So just be aware when you're doing your math that you are doing it appropriately there. All right, that's the end. Are those lines parallel? What do you think?